previous class. Now, like I said, we're going to see the solution of the exercise question 1.8. Right? So, please verify whether your method is correct or not, and let's see whether we get the same answer at the end. Okay, so I'm reading the question. It is 2-point charges QA, which is 3 microcoulomb, and QB equal to -3 microcoulomb, are located 20 centimeter apart in vacuum. Okay, what part of the question is, what is the electric field at the midpoint O of the line AB joining the two charges? So let's draw a nice diagram. Here is the charge QA, which is positive, and here is the charge QB, which is negative. So QA is 3 microcoulomb and QB is -3 microcoulomb. Okay, so that's what we know. Right? And the distance between these two charges is given as 20 centimeter. Right? So I hope you have drawn the diagram exactly like this. Don't forget, these are point charges. We can use the Coulomb's law, or we can use the formula electric field that we have derived so far. Okay. What is the electric field at the midpoint O of the line joining A and B? Right? Let's say that this is the line that joins A and B, and over here O is the midpoint. Right? So obviously this distance is 10 centimeter, and so is this. Okay, so that's what we know. Right? We have to find what's the electric field at this point O. Okay, we'll find magnitude and direction both. What I'm going to do is, I'll say that this distance, this point over here is origin, and we're going to use a simple axis, orientation, that right side is x-axis, positive x, and upwards is positive y. So again, what we have is O is over here, right hand side is positive x, upwards is positive y. So now, if I want to find electric field at O, think about which charges are going to create that electric field in this space. Will the charge at A, that's this QA, create electric field at A? Will the charge at B create electric field at this point O? So the answer is both of these charges are going to create electric field at O. So I can write that the electric field at O is actually equal to the electric field at O created by A plus the electric field at O created by B. Fair enough? Don't forget, these are vectors. Okay, please don't forget that. Now we are going to use the electric field due to a point charge formula. Right? Forget about this. Like I said earlier, superposition principle. This charge doesn't care whether there's another charge B over here. No problem. Right? Okay. So electric field at O due to A vector. Well, let me just write the formula over here. Very quickly for you, it is KQ by R square R hat. Right? But even more important is the idea to realize that positive charges over here, if you remember those diagrams, right? For a positive charge, the electric field is going to be radially outwards. Okay, it's going outwards. So positive charge, electric field going radially outwards, that's away or out from it in all directions. Okay, so at O, the electric field due to A is going to be towards the right hand side. Okay. I think you would have understood this, right? So it's very important that you do understand why we have the electric field at O towards the right hand side because of A. That OA vector should be towards the right hand side because this charge is positive and electric field is radially outwards from a positive charge, right? And if you can't recall it, I suggest you go back to previous lectures, okay, a couple of lectures, and study those very well again, right? give it one more try. So now we know the direction. Direction is as simple as. So every vector has two parts, or one magnitude, the other direction. We're done with the direction. I carried, no problem whatsoever. Now about the magnitude. So as far as magnitude is concerned, I should only worry about kq by r squared. So k, and leave it as k. Q is the charge that is creating this field. So which charge is creating this field? It's qing. So it should be 3 micro, that is 10 raised to minus 6 divided by r square, which is square of distance. Distance is 10 centimeter. Its square is 10 raised to minus 2 meters square. Right? Don't forget we are using SI units. Finally, this part, I'll write the other one very shortly. Finally, this part becomes 3k into 10 raised to minus 4 I caret. Okay. Now the other one. Okay. Now electric field at O, which is created by B. Right. So once again, we have to talk about the direction first. We are going to talk about direction, makes it easier. So this is a negative charge, right? So electric field due to a negative charge is radially inverse, that is towards the charge, right? For positive charge going away from charge, and for negative charge going towards the charge. Okay, so we have k into 3 into 10 raised to minus 6 upon 10 raised to minus 2 again into I caret. Right? There might be a couple of things that you may be surprised about. One of those is this one. Right? So let me just write the direction over here, and then we'll talk about minus. Why am I not writing minus 3 over here? Think about this. We already know that the direction of the electric field due to the negative charge is inverse. That's towards the right hand side. Okay. Now, all that remains for us, that's what we have done so far. All that remains is the magnitude. How much is the magnitude? Well, kq by r square is the magnitude. Okay. Now, when I am trying to put the magnitude, should I write minus 3 over here? No, because that minus sign is indicating the polarity of the charge. Because we are talking about magnitude, we should only write the magnitude of the charge, which is, even for B, that magnitude is 3 into 10 raised to minus 6 coulomb. Okay, so this is what we get, and finally this is again 3k into 10 raised to minus 4 I caret. So the final answer is 6k, and we'll put the value 9 into 10 raised to 9 into 10 raised to minus 4 I caret, and obviously the unit Newton per coulomb. So finally, you have 5.4 into 10 raised to 6. Use SI units, use scientific notation. So 5.4 into 10 raised to 6 Newton per coulomb I caret. That is the net electric field is towards the right hand side. Okay. Now, I want you to understand that there is one more way to handle what we have done over here. Right? I just want to give you options. Right? I want to give you choices, because it's possible that some of the students like it this way, some others may like it that way. I would still insist that you learn both these methods. You know how to do it in any kind of situation, right? So let's see how we could do it by one more method. Right? Okay. So that method, let me tell you again before we start, there's nothing wrong with it. There's nothing wrong with what we have done over here. Right? Which method do I prefer? Well, both equally. There is no choice as far as which is better. No, that's not what we're talking about. Right? So let's try to do this in another way. Right? Obviously, the answer is going to be same. I don't have to worry about it. I'm just going to use this formula blindly. Right? Okay, so let's see what happens. K upon distance squared, so 10 raised to minus 2. Right? Be careful. Now Q, if I want to use it this way directly, I'll have to not put magnitude. Then what I'm doing is, I don't know what's the direction of E or B vector. I'm not even thinking about it. I'm just using this formula, that's it. Okay. Right? So K, Q by R squared. That's what we have done so far. And now, we are going to write r hat. If you recall, when we derived this formula, r hat is actually the radial vector or radial unit vector which is going away from the charge, right? Radial vector away from charge. So that means here if I would write the radial vector going away from this charge V, that would actually be in the negative I direction. I hope you have understood what I said. And repeat, when we derive this formula, we use that r hat is the radial unit vector which is going away from the charge. So this is the charge that is creating this field at O. The radial vector due to this charge is going away from the charge, so it should go towards the left side. So the direction that we have got over here for the radial vector r hat is minus, right, towards the left side. So, and that's why ultimately two negatives are going to make it positive, and you get the same thing, 3k to 10 raised to minus 4 I carry. Right? So finally, if someone would ask you what's the direction of the electric field at O due to B, electric field at O due to B, and the answer is the direction of that electric field at O due to B is once again towards the right hand side. Obviously, the way you calculate cannot change what is happening in nature. Right? So we should not forget that we have it in this manner. Right? Okay, so I've shown you two methods. In method 1, we separated the two things. That is, we talked about magnitude separately, we talked about direction separately, we figured the direction out in the diagram, and then just put the magnitude. That was the first method. The second method is we don't worry about the direction at all at the beginning. We just use this formula and we use the defined r hat, which is the radial unit vector going away from the charge. So we just follow it that way and we get the same answer at the end. Don't forget this is magnitude again and the direction is okay. So that's for this problem, right? I hope you did it by the right method. I did this or that. Okay, and also got the correct answer. Right? It is likely that some of you got the answer 0. If that is the case, let me tell you, the mistake that you have made is the one of scalars and vectors. The electric field is a vector. You cannot simply add, right? Okay, you might have thought that, well, we are putting Q as negative and say 3 and minus 3, so the net result is 0. No, that is not how it's going to work. Okay, so remember, because electric field is a vector, it's necessary to think about directions either by drawing a nice diagram or maybe in the form of components I can take it or something like that. Okay, so please be careful with this. Right, now we are going to solve the example 1.9 from the text. Right? Okay, so let's start with it. This example will give you more practice about this same concept. Okay, so before that, I just forgot to solve part B for you. I'm so sorry. Exercise question 1.8, part B. What we did was actually only A, wasn't it? Right? We just we still have to do the part B. Right. So let me read it. It says that if a negative test charge of magnitude 1.5 to 10 raised to minus 9 coulomb is placed at this point, what is the force experienced by the test charge? So if we are going to put a test charge 1.5 in 10 raised to minus 9 coulomb, but negative at the point O. So if you just recall what we did in the diagram very quickly again. So here is charge at A, here is the charge at B, this is the point O, and this is positive, that point is negative, right? And we know this is our 10 centimeter each and all that. Okay, the question says that now we put one more charge, let's call it this one. Right? We put a charge here over here, which is negative, and 1.5. Yeah. Right. negative 1.5 into 10 raised to minus 9 coulomb. We are putting that charge over here now. Right? So how much force will act on that charge Q if it's placed over there? Right? See, this is exactly an opportunity for us to understand the role of this equation. Hopefully you do remember this relation that if we are putting a charge Q at this point O, then I can find out the force acting on that charge by multiplying the charge with the electric field at that point. That is F is equal to QE, right? So FQ, force on Q, is equal to Q into electric field at O because this charge is placed at O. Now, the other way to do it would be to use Coulomb's law. That is, you could say that this charge, just indicated here, I'm not going to do it. In fact, I recommend that you learn to do it by this method. You could do it like this. Right? I don't think you have any problems whatsoever with that. Force on Q, total force on Q is force on Q due to A vector plus force on Q due to B vector. Okay, so let's do it by this, like I've said, because we have already found out the electric field. So all I have to do is the force on Q is Q, that is minus 1.5 into 10 raised to minus 9 coulomb, right? And multiplied with the electric field at O, which is a vector. So we have got that the electric field at O is what, 5.4 into 10 raised to minus 10 raised to 6. Is that right? Is that what we have? I can't, wasn't it? The direction is I can. So ultimately, what is going to happen is this negative and this I caret is going to give us the negative I caret direction over here. So 1.5 into 5.4, I'm going to leave all that for you, right? Okay, so it's going to be about 10 raised to minus 3 Newton and some number over here. Again, like I said, calculations are up to you. It's actually going to be 54 to 15, so 540 into 70, so it was 0. So it's going to be 8.1 into 10 raised to minus 3. I caret Newton anyways. So you could see that this force is in the negative direction. Do you see that? And that's not a surprise because if you remember, what we had was for the part A, we figured out that the electric field at O due to A is in this direction, electric field at O due to B is also in the same direction. So the net electric field at O due to B is also in the right hand direction, addition of these two vectors, the same direction. So that's why, because this charge is negative, the force on that charge Q will be towards the left side. That's what our calculation is taking us. It's not a surprise, right? I hope you understood this one very well. Right? This is not the recommended method because we have already found out the electric field, right? Okay, so like I said, now we are going over to the example 1.9 from the text. This question has multiple parts. Right? Let's see where we are going to solve all these. Or should I do something for you? Okay. So the question is that there are 2-point charges Q1 and Q2, and they are of magnitude 10 raised to minus 8 coulomb and minus 10 raised to minus 8 coulomb. Actually, you can't write magnitude for minus 10 raised to minus 8 coulomb, but anyways, it's slightly incorrect over here. But what is given is there are 2-point charges which are placed 0.1 meter apart. Calculate the electric field at points A, B, and C as shown in the figure. So once again, the figure, the diagram is a part of the question. I will draw the diagram from the book very quickly. We have this positive charge here, or negative charge here, right? Okay, and this is the line that joins these two charges. Okay, Q1, which is 10 raised to plus 8, 10 raised to minus 8 coulomb, and this is Q2, which is minus 10 raised to minus 8 coulomb, right? And the distance between these two is given to be 0.1 meter, right? Okay, and the points A, B, and C are located as follows. Here is A at the midpoint of these two, right? And here is B somewhere on this side, right? And the point C is somewhere over here, right? Figure not to scale. And so this is the distances of B over here is 0.05 meter, and the distance of C from this point A is well, not given. We have to figure it out, right? Okay, but it's given that this is 0.1 meter and this is 0.1 meter, right? So it actually makes it very simple now. So we are given that this point is C, okay, and the distance of that point C from this charge is 0.1 meter, and also from that charge. So it's on the bisector, right? Perpendicular bisector. Now we have to find out the electric field at the point A, B, and C, right? So there are three questions in fact. We have to find electric field. We have to find electric field at A, at B, and at C. Okay. Out of all of these, I am going to solve the electric field at C for you, right? I will leave both of these for you to do it yourself, because I think you should practice this idea, right? Last time I asked you to solve the exercise question 128, right? This will also give you a bit more practice, right? Also, what's the reason that I'm choosing this one? Because A and B, they are all in the same line as this system, the two charges are. But C is on the side. So for C, it's going to be a two-dimensional problem. Right? I think I should help you out with that. Okay, so that it's your first time and you really learn it very easily if I do that. But yet, you could try to do it on your own. Pause the video. Okay, try to do it on your own. Let's start. So first of all, we're going to draw the vectors over here. Electric field at C. Who is going to create electric field at C? That's the question. Well, how many source charges could be there? Well, 2, 1 and 2, positive, negative, right? So electric field at C due to the first charge plus electric field at C due to the second charge, right? I think that's dead simple now for you. Okay, so we're going to draw these arrows, these electric field vectors. This is a positive charge. Remember the sentence I told you about. Electric field due to a positive charge is radially outwards or away from this positive charge. So over here, this electric field due to the positive charge is going to be in this direction, that is EC1 in that. Correct? Okay. Similarly, for the negative charge, well, the electric field is radial, but not radial outwards, rather radial inward, that is towards the center. Okay, so the electric field due to the second charge is EC2, it's exactly along this line, towards this charge, right? Again, this distance is 0.1 meter, okay. Now, based on that, we have got one electric field over here, the other one over here, so we have to find out the resultant. Don't forget, we are doing a vector addition, so we have to find out the resultant. Okay, but because of the symmetry of the situation, I'm sure you realize that if we use the parallelogram law, we are going to get that the electric field, net electric field at this point C will be exactly towards the right hand side, that is, in this direction. Okay, from the positive to the negative charge, in that direction, right? Okay, so I think that's pretty clear. Okay, based on the parallelogram that I've drawn here, and now we are going to find out the magnitude. We have figured out the direction, so we are going to find out the magnitude, right? So do you realize that if I want to add two vectors resultant magnitude, we have to use the well-known formula. That's why I used to say it again and again that 11th standard physics is very important if you want to understand it well. Okay, so this is what you know. The only thing that remains is to figure out what's theta. If you remember in that formula for the resultant magnitude, theta is the angle between the two vectors. So we have to find out what's this, and we have to find out its cos. Okay, and we have to find out what is its cos. Now, what you would do here is, this is especially for biology students, instead of finding cos theta, you may also find out this half angle, right? So let's say this whole angle, use a pen here. This whole angle is theta, okay? But I could split that angle into two, like this, right? That will definitely help with the calculations. I'm doing this specifically for biology students. Okay, it is. I think it's fine really for the math students. You wouldn't have any problems whatsoever. So what I'll do is to find this angle theta by 2. Find the angle theta by 2. I'll go over here because this angle should also be theta by 2. Have a look at this diagram once again. Right? We have a line coming in all the way from here like this. So whatever is this angle, the same angle should be theta by 2. Right? So if you are familiar with trigonometry relations, then you will do it by this problem. I mean this equation, right? So otherwise, we'll have to take a slightly longer but easier route. Okay. So this is how it will work out. I know that the net electric field is towards the right hand side. So I'm going to only add the electric field horizontal components. That's it, because of the symmetry. See, symmetry. This is 10 raised to minus 8 coulomb. This is also 10 raised to minus 8 coulomb in magnitude, right? So the magnitude of these two electric fields is the same. Understood? Right? So what is happening is that the net electric field is going to be towards the right hand side. Only in the ICAD form, only, excuse me, I just have to correct this one here. I made a mistake. I have to take the components of the field towards the right hand side. So that is EC1 cos theta by 2 I caret plus EC2 cos theta by 2 I caret again. Right? So you have understood that we are taking component of this EC1 vector towards the right hand side. Okay, because this angle is theta by 2. Right? So the same thing about EC2. Right? So what we are going to do is, if we find out cos theta by 2, then it's going to be easy. So this is theta by 2. Look at this triangle. If I want to find cos theta by 2, if I want to find cos theta by 2, this is the adjacent, which is going to be half of 0.1, so it's 0.05. Right? And cos is obviously adjacent divided by the hypotenuse, so the hypotenuse is 0.1. Okay, right? Fine. So what we have is that this is obviously 1 by 2. Is it fine? And that allows you to put these values over there. Cos theta by 2 is 1 by 2. Now what remains is to figure out what is EC1 and EC2. See, the magnitudes are going to be same because the charges are same and these distances are also the same. So EC1 and EC2 have same magnitude, and that is going to be equal to, right? What's the formula? Is K into Q by R squared. Right? See, this is the magnitude of electric field again. I hope you were not expecting to write that. No, because magnitude, right? We don't want to worry about the direction. That's the formula. Let's use it here. So over here at Q, I should be writing the magnitude of the charge, which is 10 raised to minus 8 coulomb. Right? As far as R is concerned, I should write the distance between that point C and the charge 1 or the charge 2. Either way, the distance is 0.1. So KQ by R square is the magnitude of electric field. Okay, clear? So again, let me just summarize it quickly. What we have done is that at this point there are two electric fields going here and here. We want to find the resultant, so we could have done it like this. Okay, by using the resultant magnitude formula, right? The problem would be we don't know theta. So obviously, math students could have done it by using a trigonometry formula that they have studied, right? But otherwise, you could do it by taking components of the electric fields at C, right? DC1 and DC2 components. So in the right hand direction, because we know that these two, because of the symmetry, they give it with the right hand side. So we put EC1 and EC2's magnitude back into this equation. Cos theta by 2's value is half. We put it back over there. So finally, we get that EC vector is equal to, right? See, everything is same over here, so I could just double it, right? Magnitude same, cos theta by 2 is same, I carry same. So 2 into EC1 cos theta by 2, right? Okay, don't cancel these two with the 2 up there. So that's a big crime, don't forget that. So 2 into EC1 is this. So K into 10 raised to minus 6. Right? Okay, all calculations done, and cos theta by 2 is half. And so finally, you cancel now ultimately, and then you get 9 into 10 raised to 3 Newton per Coulomb, and in direction I carry, right? So that is the electric field at the point. The key thing over here again is you can't add the two directly. This would be extremely wrong. Okay, you can't do that because electric field is vector. You have to be careful about the direction of it. Right? So please don't make this blunder. Right? So that's it. We're done as far as the electric field at C is concerned. Like I said, we have to do the electric field for A and B. You have to find both of these on your own. Right? Okay, so that's it for this problem. Right? Now we will solve the exercise question 25. Right? We're going to solve the exercise question number 25. Let me take this one quickly. It's one of those additional exercises problem, but don't be scared by it. And it's not that additional exercises are always difficult. Sometimes they are. Physics could be a bit troublesome. Right? Okay, so let's start. So the question is that an oil drop of 12 excess electrons, excess that is extra, right? First of all, let me just write that over here. Excess that is extra. Okay, so it has 12 electrons more than what it should have. Okay, it has 12 electrons more than what it should have. Right? And it is held stationary under a constant electric field of 2.55 into 10 raised to 4 Newton per Coulomb. The fact is that what is happening is that at some point in space, we have created an electric field, right? We have created an electric field, and that electric field is 2.55 into 10 raised to 4 Newton per Coulomb, right? Okay, and here we are holding an electron because of the electric field. That is, we have left it on its own. But it's not falling, right? That is what the question says. An oil drop of 12 excess electrons is held stationary under a constant electric field at some point, and the magnitude is 2.55 into 10 raised to 4 Newton per Coulomb. And this experiment is obviously the Millikan's oil drop experiment. such experiments were used to establish properties of basic charges like electrons very early, typically to find out the charge and mass ratio. Right? But anyways, it's that the density of oil is 1.26 gram per centimeter cube. So this is, it's not just one electron, but there are 12, right? 12 excess electrons over here in this oil drop. The fact is that the oil drop will have lots of charges, but under normal circumstances, everything is neutral. Right? Atoms are neutral, but in this experiment, for this experiment, somehow we have charged a drop of oil, and this charged drop of oil has 12 excess electrons, right, in this oil drop over here. So what we are doing is we are creating an electric field which is downwards. Right? How do I know the electric field is in downwards direction? You might have a question like that, but the answer lies in the fact that this is a negative charge. So the force on the negative charge should be opposite to the electric field. Electric field downwards, so the force on the negative charge should be upwards, right? And that's why what will happen is, and if I draw FBD of oil drop, which has 12 excess electrons, the electric force is upwards. Is that okay? The force due to the electric field or the electric force is upwards, but because the oil is over here on Earth, right? The oil drop, it will have mass and it will also have a weight, that is mg, will be acting downwards. So why is this drop held stationary on its own? Because these two forces exactly balance each other out and it is in equilibrium. So ultimately we have Fe is equal to G, right? We have Fe is equal to mg, right? Now what are we doing? If we are given the density of oil, we could use that maybe to find the mass, right? And estimate the radius of the drop, and it is given that we have to use G is equal to 9.81 meter per second square. We have to use charge of electron E as 1.60 into 10 raised to minus 19 coulomb. So what we are going to do is we are going to put the mass based on density in electric, right? So density as well, rho density of the oil is given to be 1.26, but be careful, the unit is not SI, it's G, gram per centimeter cube. So if we convert it to SI, it's going to be 1.26 into 10 raised to 3 kg per meter, right? So that's what we know about the oil drop. So let's put all these values so that we can ultimately find out what's the radius of the oil drop. Okay, force, electric force, right, on this oil drop. See, the oil drop has a charge. How much charge? It has a charge of 12 electrons, right? Because other things being neutral, right? Only these 12 extra electrons are going to create the net charge of 12 electrons. So the charge of the electron on the 12 electrons is going to be 12e. Okay? Force on a charge in an electric field is Q into E. Right? So what's the value of E? It's 2.55 into 10 raised to 4. Okay, I hope you are surprised by this. We are using F is equal to QE, right, in magnitude form. Okay, so this is the charge on the oil drop, this is the electric field. That is equal to mass into G. Now G obviously is 9.81, but as far as mass is concerned, we are not given the mass. So what we have to do is, we have to somehow link all this with the radius. Density is given, mass is given, it's a liquid. I'm sure you can figure it out easily. You should write mass as density into volume. Okay. And ultimately, volume can be written as 4 by 3 pi r cube, because oil drop can be assumed to be spherical, right? the problem. Right? So find out the volume from this equation and we put it over here and then we can find radius. So the volume is going to be 12 into 1.6 into 10 raised to minus 19 into 2.55 into 10 raised to 4 divided by density, which is 1.26 into 10 raised to 3 into G, that is 9.2. Right? I don't think you have had any problems with it so far. Okay. So we put the mass as density into volume for the liquid. We put volume as 4 by 3 pi cube. And clarify that again. We are assuming that the drop is spherical, which is a reasonable assumption. Okay. So from this calculation, you are going to find out R. Right? Put all these terms on the other side, and you will get your answer. Right? So that's it for this problem. Like I said, although it is an additional problem, see, the method isn't that difficult. All you have to do is you have to use the concept of force acting on a charge inside an electric field, and that's it. Right? The rest is very simple. Okay, so that's it for this part of the chapter. Right? And now I don't like to give you. I don't like to teach you any further concepts in this part of the lecture. What I'll do rather is I'll ask you to solve some extra problems that I'm going to put on the board. Okay, so let's start with that. Here are some extra problems which are related to the finding the electric field and the forces charged due to electric field. So here's question 1. Suppose that over here at the points A and B, which are 1 meter apart, right? Over here there is a charge 4 microcoulomb, and at B there is a charge, say, 1 microcoulomb. Okay, and distance between them is 1 meter. You have to find the distance of point and the distance of the point where electric field is 0. Find the distance of the point where electric field is 0 from the point. And the distance of point from A, where the electric field is 0. Okay, so what you have to do is these two are one straight line, and at some point on this line, you're going to have that the electric field is 0. Right? You have to find the distance of that point where the electric field is 0. I don't know where it is. It could be right here in the center. I don't know, right? You have to find it out. Where is that point? Okay, I'm just showing the center thing over here, just indicating this, right? So you have to find what's the distance of that point from A, wherever that electric field is 0. Okay. So second question is a similar question, right? The only difference being it's going to be a negative charge. Right? Let's say that once again there are points A and B, and at these 2 points you have being given charges. We'll say this charge is 2 microcoulomb. Right? Let's say that this charge is minus 4 microcoulomb. Okay, and now if the distance between these two is let's say 14 meters. Okay, right. So same question. First of all, is the electric field 0 at any point? That's the question. Is the electric field 0 at any point? Okay, so first you have to check whether the electric field could be 0 at any point or not, and if yes, find the distance of that point from A. So once you solve this question, I'm going to ask you to solve the third one, where we will talk about electric fields in 2 dimensions, so you get appropriate practice for that as well. So let's say that there are 2 positive charges, Q1 is 3 microcoulomb and Q2, which is again 3 microcoulomb, both of being positive, and you want to find out the electric field at this point A, which is at distance of 1 meter from here. Let's say that the distance between these two is also 1 meter, and the same over here, right? So the question is, find the electric field at A. Right? Don't forget, electric field is a vector. You have to find the magnitude and the direction as well. Again, the best way to do it is to draw the electric field vectors in the diagram, right? Okay, so that will definitely help you out, right? Now, like we've seen, these questions are for electric field combined or net electric field due to 2 charges, right? But obviously the same principle applies when you have to find out electric field due to more than 2 charges, right? So here is one such question for you. Okay. Let's say that let's square, right? Right, so this is the square of side 2 meter, and at each of these corners there is a charge. Let's say there is Q1 here, Q2 over here, Q3 over here, and Q4 over here. Okay, now the question is, find net electric field at the center of square, that is at intersection of diagonals. Okay, so that is where the diagonals intersect. You have to find the electric field at that point. Okay, it's given that Q1 is equal to 1 microcoulomb, Q2 is equal to minus 2 microcoulomb, Q3 is equal to 3 microcoulomb, and Q4 is equal to minus 4 microcoulomb. Right? So you're given these 4 charges, okay, and you have to find out what's the net electric field at the intersection of the diagonals, right? Okay, so that is what we have for this problem. Right? I'm going to give you the answers and hints to all these problems tomorrow. So tomorrow by 5 p.m. So you make sure you please practice these questions in that time and get to the final answer, so that later on when I give you the answers or the hints, you verify whether your answer is right or wrong. Supposedly, if you are wrong, you could just check whether you have followed the hints that I've given in the along with the answers, right? I hope you have done by the right method, but just in case there's some problem, you could verify it, you could get it correct. Okay, so I think that's all for this lecture really. Okay, make sure you solve these questions because it's necessary to practice all these things, right? That will give you a firm grip of what is to follow in the next part of the chapter, right? So that's it for now. Goodbye, everyone. I hope that you're going to enjoy this physics journey as we go through all these interesting concepts.